Chapter 1, Lecture 2, Introduction and Basic Concepts. Temperature scales. All temperature scales are based on some easily reproduced property, such as the freezing and boiling points of water. So here it shows a graph. We have the four different temperature scales that we use: Celsius, Kelvin, Fahrenheit, and Rankine. Celsius and Kelvin are the metric systems. Fahrenheit and Rankine are the English systems. So first of all, let's understand what the ice point is. So a mixture of ice and water that is in equilibrium with air saturated with water vapor at 1 atmosphere. The ice point is 0 degrees C or 32 degrees Fahrenheit. The steam point is 100 degrees C or 212 degrees Fahrenheit. So that sets those scales. So for example, on the Celsius scale, you see here is 0 degrees for the freezing point of water. Here's 32 degrees on the Fahrenheit scale. Here's the boiling point of water, 212. Here's the boiling point of water on the Celsius scale, it's 100 degrees C. There are two other scales, the Kelvin scale and the Rankine scale. These are the absolute scales. And so they're defined to be, the Kelvin scale is Celsius plus 273.15. We typically just round this to 273. The Rankine scale is equal to the Fahrenheit temperature plus 459.67. We usually just round this to 460. You can convert between Kelvin and Rankine and Celsius and Fahrenheit using the following two formulas. One thing to keep in mind is also the change in temperatures. So for example, if you're in the Kelvin scale, the change in T is equal, Kelvin is equal to change in T temperature. It doesn't really matter at that point because the constant's subtracted off. Same thing with the Rankine scale. Delta T Rankine equals delta T degrees Fahrenheit. Okay, let's take a look at the manometer. The manometer is commonly used to measure small and moderate pressure differences inside of a fluid. Manometer contains one or more fluids such as mercury, water, alcohol, or oil. So the key to understanding how a manometer works is to understand the slide on the left here. So again, if we start at atmosphere, if we go downward and we want to find the pressure at 1, what we need to do is just add up all those pressure differences as we go. So notice fluid 1 has a different density than fluid 2 and then fluid 3. So I can see if I can draw this here for you. So let's say this is row 1. This is the pressure, the density in that fluid. Here it's row 2. Again, it's hard for me to draw a 2 using a mouse. And the fluid 3 is row 3, let's say. And the 3 is really hard to draw. Okay, that's pretty good. Okay, so now let's say we start at P atmosphere. So if we're going, all we need to keep track of is the vertical difference as we go down. So if we go start at P1, the pressure right at the interface at P2, fluid 2, is P atmosphere plus rho 1 G H1. H1 being the depth from surface to where the interface is. And then we continue that process all the way down. The pressure difference here, we just add on rho 2 G times H2. The pressure at 1 then is going to be just the sum of all these values. So the pressure at 1 is going to be P atmosphere plus all these terms, rho 1 GH1 plus rho 2 GH2 plus rho 3 GH3. It's pretty easy to see, if you just have different fluids in a beaker or something like that, how the pressure down here is just the sum of everything on top of it. I think what gets confusing for students is when you have a situation like the right up here. When you have these bends and stuff like that. So let's say we have a pressure here that we know, and then we want to find what the pressure is on the other side here due to this fluid flow. Well, what we do is we put this manometer in. Notice how the manometer has two fluids, right? There's a fluid here that's inside the pipe, and then there's a heavier fluid here. Maybe this is mercury. Let's call this rho 2. So what we have to do, we start at at 1, at pressure 1, all we need to do is keep track of the height, the vertical height difference as we go, increases and decreases as we go from here all the way around up to here. So the pressure, let's find the pressure at A first. So the pressure at A is going to be equal to the pressure 1 plus rho 1g times the height difference from A to the surface here, to 1. That difference is A plus H. So the pressure at A is going to be equal to P1 plus rho 1g A plus H. That's the pressure right there. Now, so let's get this little loop here. But you're going to increase in pressure as you go down, but you're going to decrease in pressure as you go back up by the same amount. So what that amounts to is that horizontally, as long as the fluid's the same, this is all the darker red area, you can just sort of jump from here to there. The pressure at A is going to equal the pressure at B because it increases and decreases by the same amount going from A to B. So now we're here. Now, if we go from B up to 2, we're going to decrease in pressure, right? Well, by how much? Well, it's going to be the pressure here minus rho 2gh. That gets us to here. And then going from here up to there, we subtract off a rho 1g times A. So if we keep track of all those increases and decreases as we go along, we end up with this formula here. But you can see how I did that. I mean, it doesn't matter what it looks like. This started somewhere, and if you go down, you increase in pressure. As you go up, you decrease in pressure, and then you can write these terms out pretty simply. Notice also you can subtract this difference. So if you want to know the pressure difference, you solve this equation here for P1 minus P2, and you get this thing here. Because some of the terms cancel. This part will cancel that part, for example, and you'll be left with this. You can also do, a very basic manometer where you have, this is open to atmosphere. So you do exactly the same thing, though. You start, pressure 2 is P atmosphere plus rho g H, right? Because up here's P atmosphere, right? So you're going to go down. How much do you go down? Well, you go down H amount. So it's rho, which is the density of the fluid, times GH. And then you can jump right across to here because the pressure here is the same as the pressure there because it's the same fluid in the bottom part. And so since this gas is connected to that, it's pretty easy to find that. P2 is equal to P atmosphere plus rho g times H. There's a lot of other ways to measure pressure. There's what's all these Bourdon tubes. There's pressure transducers. Strain gauges. There's also piezoelectric transducers. All these kind of different devices are used to measure pressures in fluid systems. Barometer, this is our last slide here. Barometer and the atmospheric pressure. We sort of, we wake up, we look at the weather, a lot of us do anyway, and we pay attention to what the barometer is for that day. Well, the barometer it's just atmospheric pressure that's measured by a barometer. This we call it barometric pressure. Frequently used pressure unit is what's known as the standard atmosphere, which is defined to be the pressure produced by a column of mercury 760 millimeters high at 0 degrees C. So that's pretty much what it is. P atmospheres, rho GH, same kind of thing here. You just got mercury in here. If you take a bunch of mercury and you take a long tube and you stand it up like this, you'll find this height is roughly 760 millimeters at 0 degrees C. It may move around a little bit depending on the weather, but not drastically.